All right, let's get started. Hopefully everyone had a good weekend. Yeah. Some of you had a longer weekend than others. Amanda mentioned, and I'm glad you did, because this morning I fixed it. I wasn't recording the audio, so if you're out there looking at the video from last week, it's just a lot of visual. So from now on, hopefully audio will come with it, as long as we maintain a reasonable amount of attendance here, which we have so far. Oh, don't worry. Yeah, come on in. Take it. There isn't another one?
No.
Wow.
There's like maybe
Yeah.
corner, I think there's one.
Okay. So last week we kind of have been walking through what is this idea of the finite element method, right? Finite element analysis. Talked about kind of it's this numerical solution to a field problem, right? And the field problem is basically looking at something that varies over some sort of space, right? In our case, it might be an element, it might be the height of a column, okay, the length of a beam or something like that. And that field variable varies, right? And is a function of a integral or some sort of derivative, okay? And so as we're working through this, when we get to the practical implication of field variables, right, we talked about a couple examples, which would be a frame or an axially loaded bar for us as structural engineers. Okay? Practical implication of field variables, right, is that we are going to calculate one variable, right, which would be, say, deflection in a beam or a frame or rotations. And a lot of the things that we're looking at as structural engineers are interested in is some of the other things like forces, right? Moments and shears, things like that. Things that are derivatives or derived from our field variables. And so all other results given by programs, right, that are not the field variable are derived, are based on those field variables. And these derived values are often based on the derivatives of the field variables, and therefore they're often less accurate, right? So values are often based on derivatives of our field variables, and therefore they're often less accurate. If I can spell. So these field variables, coming up with what those field variables are. We also have desired results that are outside of those field variables, right? Things that are a function of those field variables, and the fact that we take that additional step or multiple steps, we get varying or further away from the real answer, and we're going to look at that here in a second, okay? So why do they call it the finite element analysis? Well, as we mentioned, we're breaking our problems up into finite, right? So let's look at the solution process. How does that start? Well, the first one is, as I mentioned, splitting up our problem into finite regions. Right, when we do our mechanics of materials formulations, when you guys are in mechanics of materials, right, if you had a indeterminate beam, right, we start looking at how deflections result, right, in order to get solutions. And when we did that, we take integrals, right, and integrals are an infinitesimal, right, breakup of a member, right, dx, dz, all of those things. We're breaking up our element into infinitely small portions, and so our solution is based on that. Well, in the finite element process, we split the problem into finite regions, right, that have defined length. So we connect now these finite regions, or what we would call elements. So we connect each element at what we call nodes. Right? So we see the frame up here, right? The nodes being the ends of our element segments. Once we have split up our system into finite regions, right, into elements, those finite regions have nodes on them, we really just solve a set of algebraic equations to determine our nodal values. Of this field variable, right? If it was displacements or rotations, we break it up into these finite regions. We connect them at nodes. Do a bunch of background algebraic manipulations and calculations to figure out what's going on at each one of those nodes, right? The intersection of each of the elements. Once we know what those nodal values are, we can then just use simple interpolation functions to define the field between nodes. Right? As I've mentioned the last few days, essentially that is what the finite element method is, right? We're breaking it up into finite regions, we connect them at nodes, we calculate what the values of our field variable, right, our parameter that we're looking for at those nodes, and then we made some assumption as to what we think that field variable, how it varies from one node to the other, okay? And we call that an interpolation function. We'll talk about that more too later on. So as mentioned, the finite regions give finite element analysis its name. So if we had this field variable phi, right, and it varied over space, our green line would be, say, our exact or actual solution. This would be our actual solution. Right, this nice clean curve that varied as we move through space, right, along the length or over an area or surface. This field variable might be displacement, might be rotation, might be temperature, okay? And as we divide our system into finite regions, we would call them finite elements. Right? And those finite elements are connected at what we would call nodes. And once we knew what our nodal values were, we would have an interpolation function, right? An idea of how the displacement changes from one node to the next, right? Based on our nodal values. So this would be our approximation or FEA approximate solution. Right, those are our straight lines between nodes. And we went through the case studies, right? Sometimes our assumed interpolation function or assumed behavior of our field variable between nodes might be linear, might be a straight line, it might be a polynomial, right? So in this case, it might be a linear. So we go straight line from node to node. That would be our FEA approximate solution. And as you can see from this curve, right, we really have a simplification of our real behavior, right? What's really going to happen. Based on the fact that we don't have this continuum or this continuous function of the actual solution. Right? But as you can imagine here, if we were to break this up into 10 times as many elements as I do, right, we get closer and closer to this curve. So this idea that if we got to infinitesimal size elements, we would get really, really asymptotically approach. We'd get as close as we possibly could to the real solution, or really our modeled solution. We'll talk about that in a second too. We talked a little bit about it last week, the fact that we're making assumptions along the way. We're simplifying the real world. Right? The real world is very complicated. So let's just do a little very simplified example. Okay. This is a real structure somewhere. Okay, I went out and found it somewhere just to try and give some context to the example we're going to do. But we have a concrete structure, right? And it ends up down at the bottom with this one concrete column. Okay. And if we looked at a concrete column, so let's consider a tapered column in our case, right? And it supports a beam or some other structural elements at the top of it, right? We're supporting a beam with bearing reaction, okay? A bearing reaction, we call it P, right? It's on top of a tapered column. Tapered column sits on a footing, right? Which then sits on soil, right? That's our bearing strata. Supported by a footing and then dirt below that. And if we were interested in, as we normally are, right, a field variable, we're going to look at displacement. Also, as structural engineers, right, we always are interested in stress also. So we were looking at this tapered column, and we wanted to know the displacement of this column and the stress in this column, right? Based on this applied load and the support conditions that we have, right? This was what we would be calling, right? This is the real world. This is what we would look at as structural engineers. This is what an architect would give us. Say, hey, we love the look of this tapered column. Okay, even though you tell them that this is ridiculous and it'd be really expensive, right, and impractical for a contractor to do a tapered column, right? But they say it makes the room feel good, right? It's going to add to the overall feeling of the structure, all right? And we have to analyze this. We'd be interested in displacement and stress. So our next step would be to develop a model of this, right? We want to simplify without being too simplistic. Right? We want to capture the behavior that we want without oversimplifying and not being as accurate as we need to be. And this is where we get into this experience world, right? Like, how do we simplify this without going too far? Okay, good judgment comes from experience. Experience comes from bad judgment, sort of thing, right? So we need to develop a model of this. Well, if we assume that our load becomes P, this point load, right? Pretty gross assumption of our loading, right? In reality, like we talked about last week, with our simply supported beams, right? A pin reaction at the end of our structure, right, is a pretty big assumption also. In the real world, there's going to be some resistance to rotation. There's going to be other forces in there that we are ignoring, okay? So in this case, we looked at P. We're going to assume our complex behavior. can just become a point load. Right? For those of you that took Ladine's class, you had a project, right?
We actually did not do the project.
What?
Yeah.
That was like the best part of that entire class.
I know.
Wow! What was his reasoning?
We just ran out of time.
Oh, okay, I can see that happening.
We asked too many questions.
Yeah, way to go.
Yeah.
Nice. No project. Man, you guys are smart. I gotta watch out for you guys, huh? I'm gonna drag this on so we don't delay, yeah, until you can't do it anymore. I get it. I get it. I'm on to you guys. All right.
I have a question.
Yeah.
Where
Man.
the footing meets the, I'm sorry, where the column meets the footing, what is that symbol like next to the A?
Oh, sorry, that's 7A. So, no, good point. So this is, it's a tapered column, right? So we're trying to find a relationship between the cross-sectional area at the top of the column to the cross-sectional area at the bottom. That defines the taper. And so at the top, we're gonna say it's 1A. At the bottom, it's 7 times that area.
Okay.
Right, so it goes from A to 7A. No, good question. I didn't mention anything about that, so. All right. So with respect to load, we make this assumption, right? We're gonna have some sort of column or member framing into the top of this tapered column. And we're gonna make the assumption that all of that can be boiled down to just a point load, right? Which is pretty gross assumption, but we're going to make it. Now, we have this concrete, I don't know if I called it concrete, yes, concrete tapered column, right? Any ideas on what assumptions we make about materials a lot of times, especially when it comes to concrete?
Uniformity.
Uniformity, exactly, Elias. We're gonna say that it's homogeneous, right? We're gonna say that it's linear elastic. Concrete cracks. I think you're just never gonna get away from that. So the fact that we're assuming that it's linear elastic, and then we put rebar in it, so assuming that it's homogeneous, are pretty gross assumptions also, but prove very well for the most part in analysis programs. So we're gonna assume that it's linear elastic and homogeneous. Any ideas how we could assume that the weight of the column is nothing? 0?
So E is really big.
Yes, exactly. Right, in contrast to the applied load, the self-weight is going to be very, very small. So we're just going to ignore it. So we're going to say assume our P is a lot bigger than W. So we're going to neglect it. That greatly simplifies what's going on here, right? We had to take into account the fact that this thing had weight to it, and as we moved down this column, that weight increases, right? Greater and greater significance as we move down the column. What do you think we can assume with respect to the stress in our column that would simplify things?
Linear stress distribution.
Let's say uniaxially distributed, right? We assume that the stress is only acting in one direction in this column, just vertically. Don't have to worry about stresses acting in the perpendicular direction, so I'm going to assume uniaxial state of stress I before A. What assumptions that can we make that simplifies things on the footing, on the base? Just a guess, give me a guess. What does it look like here? What's the difference between this and this?
Not in the ground.
Yeah, I mean, we essentially, I deleted the footing, and I said that it's just fixed at the base. Right? That's a huge assumption also. And so assume footing and the ground below create a rigid support. Also, we're going to assume that this support at the ground creates a uniform stress across the cross-section also. Okay. Which is also important. If we had a stress concentration that happened at one area of the base of that column, right, that would complicate things also. So overall, what does the model do? Well, the model just essentially seeks to exclude all the superfluous detail, right, but includes all the essential features so that the results describe the actual problem with sufficient detail, and this is where experience comes into play, right? If you guys were forced with calculating the displacement and stress of this column, would you guys have made these assumptions? Maybe, right? We make them a lot, and we do that in a lot of problems that you've already seen, right? Whether you're in practice or in academia. Right? That allows us to simplify problems, okay, and make them easier to assess, but not oversimplifying them, that we're getting away from the real behavior that's happening. Okay? So here comes the long one. Seeks to exclude extra detail but includes all essential features so results are sufficiently accurate with respect to the field problem. We want to assume that there's some taper in this column, right? If we didn't, then that gets away from the idea that we're looking at stress, right? An area affects stress greatly, right? So we wouldn't want to make some assumptions that had to do with the stress, right? We wouldn't want to mess around with the material too much, right? Material has a lot to do with strains, okay? So we're trying to make simplifications without oversimplifying and getting away from what we're trying to calculate in the first place. In our case, this is displacement, right? And stress. If we were looking at thermal properties, right, that would have changed our way that we made the simplification to the model in the first place, right? We'd want to be very accurate with respect to the material, right? The rebar is going to affect how our say thermal conductivity works across the column and things like that, and that would have changed our simplification. So it all comes back to what are we really after? We got to think about that first. So we took the real world, we simplified it, right? Came up with a model, and now we're going to take that model and we're going to discretize it. We're going to separate it into finite regions so that we can analyze it, right? Via the finite element method. So we're going to divide our taper into a series of prismatic elements. So if we start out, with this tapered column, right, linear taper from an area of A down to 7A, okay? I'm gonna discretize or separate this column into 3 separate finite regions that are prismatic. Okay, we're gonna start with an area that's 2 times A, go to 4 times A, and then finally 6 times A. This model can then become just a linear 1D model where we have P at the top, and we have a series of 3 elements, right, that change in area from 2A to 6A. Each of those elements are a third of the length, right, having length L, or the total length. So this is where we divide into a mesh of finite elements. I cannot seem to spell this morning. Okay. We're going to divide into a mesh of finite elements. Any ideas of, through this process, right? We started at the real world, then our model, and then discretizing our model. In these steps, where we might find error, like just globally, think big picture. 2 of these steps create error, right? First one is our jump that we made from the real world to the model. So when what we would call our modeling error, if we left something out that didn't get us that sufficient detail that we needed to get sufficiently accurate results of our field variable, right? So we would call this our modeling error. We made the jump from the real world, what we're seeing outside, to what we write down on paper on what we're going to analyze. And then again, when we start with our model, then we jump to our finite regions or our discretizing. So we get discretization error. I could have separated this into 100 elements, right? Been a lot more detailed. Okay. So making that decision to divide it into 3 versus 300 makes a big difference in our discretization and the error that we're going to impose based on the model to our analysis, right? Mike wanted me to put this quote in here. He wanted me to call him out as the person that told me to put this quote in this notes for you guys, okay? Just a heads up. Right, structurally, have you guys seen this quote before? Okay. Right, structural engineering is the art of molding materials we don't wholly understand into shapes we cannot precisely analyze so as to withstand forces we cannot really assess in such a way the community at large has no reason to suspect the extent of our ignorance. And that is truly what we do. It's just crazy, but it is. It's an educated guess. What we do is an educated guess.
With practice and safety.
Yes. But it's an educated guess still, right? So there's error in everything that we do because we cannot model the real world, right? Based on not truly understanding what the materials are. That column out there, we might think is, tube 46 KSI, right? But in reality, it might be 52 KSI. We made all these assumptions based on what that is. We get into seismic design, overstrength, right? The fact that the material is stronger than it is a negative on us, right? So we make some assumptions on what the magnitude of that is, kind of massage our calculations and what our analysis and our designs based on assuming that we know the overstrength. We have no idea, right? There could be an inherent flaw in something in there that we assume is not there, right? So we're guessing. We're guessing. But what we're doing always has to be defendable. That's the big thing, okay? Once we have discretized our model, then we can make choices as to what elements we might use, right? We're going to separate this into 3 distinct regions, right, or elements. So we're going to pick an element based on that allows us to determine what the field variable is, right? And gives us sufficient detail, right? Doesn't go too far, doesn't have too many inputs or requirements. And so in our case, when we're selecting an element, we would want an element that follows our uniaxial assumption, and that provides us with axial displacement and stress. Right, these are our desired outcomes. We know stress is a function of strain, which is a function of displacement. So if we really get an element that gives us displacement, right, axial displacement, we can derive the rest, right? We have a constitutive relationship, our Hooke's law, which will relate the stress and strain. So I'm going to consider a bar element, okay, and consider the element in the our element in our tapered column is a series of 3 bar elements. Our bar elements that I'm going to look at, we're going to derive some of the portions of this, okay? We're going to first look at our bar element between nodes 2 and 3. Okay? And this bar element, right, is needed to interpolate the axial displacement between nodal values. Right, and this axial displacement is our field variable. Right, so this bar element that we've decided to use is going to have some sort of interpolation assumption as to how does the displacement change from one node to the next node. Okay. And that constitutes a finite element, right? You have an element that's connected between nodes. These nodes have degrees of freedom, right? The ability to move. And then we assume, based on the derivation of the element, how those, that field variable, right, or those degrees of freedom change as we go from one node to the next. So let's go through the derivation of one of these, okay? So if we go through and we're going to look at this 4a bar element, right? We're going to assume, okay, we're going to use a bar element. That's going to represent our field variable, which is displacement between nodes, right? We're going to look at what's going on between nodes 2 and 3. So if we look down here, so we've got node 2 and node 3. We're going to assume our space variable, right? Our distance that we travel from one node to the next is this variable s. Okay. So when s equals 0, we're at node 2. When s equals L, we're at node 3. Okay, simple enough. And we know that if we looked at the displaced, right, so this would be undisplaced. And this would be displaced. We're going to look at our column, right, or this element, in its displaced form where we allow some degrees of freedom of our element. Right? In this case, we're interested in axial displacement. So we're going to look at the displacement of each of these nodes in the one direction. Right? So node 2 can move up, node 3 can move up. And those displacements we're going to call U2 and U3. We're gonna get into shape functions and things like that probably at the end of the week. But for now, we're gonna make this assumption that the displacement varies linearly between nodes, right? So there's a straight line distribution of displacement between nodes. That might not be accurate. But it's going to be close. So if we have a straight line between our two nodal values, we know that an equation for a line mx plus b, right? Slope times a variable plus some sort of constant, right? We've got to start at a point. So if we substitute this variable a1 as b and a2 as m and s, right, as our space variable, that's our distance along or our dependent variable as we move from one end of our element to the other. Right, where I said if s equals to 0, we're at u2, and if s equals to L, we're at u3. Our equation then becomes, if we're going to come up with an equation for the displacement from one nodal value to the other nodal value of our bar element, right? Our equation for displacement with respect to s of this just becomes a1 plus a2 times s, right? It's the same thing as the equation of a line. Now we made some substitutions for some variables to get into the nomenclature of the finite element method. Okay, this A1, A2 value.
That's just for matrices later, or what?
Yeah. And generally what we call these A1s is where A1 and A2 are known as generalized degrees of freedom. DOF, right? Degrees of freedom. They're not actual degrees of freedom, and we'll find when we start looking at shape functions and things, and when we make assumptions for displacements, our assumptions we're allowed to make are based on the degrees of freedom that we start with. So our generalized degrees of freedom, we have the same number of generalized degrees of freedom as our actual degrees of freedom of our element, right? So if we can displace, U1 can displace, right, in one direction. We have U2, which also displaces in the same direction. We have 2 degrees of freedom, right, for our element. One node can move in one direction, the other node can move in that same direction. So we have 2 degrees of freedom. We have 2 generalized degrees of freedom when we come up with our displacement assumption. So we have an A1 and A2. And that's why we make the assumption that it's a linear behavior of displacement between them. Okay. All right. So based on that equation there, right, we have an equation that has 2 unknowns. We have this generalized A1 and A2. Based on that, we can solve for A1 and A2 based on boundary conditions. Okay, we know what the values of A1 and A2 are based on knowing the value of displacement at 2 locations, right? We know that the displacement when S equal to 0, right? Our displacement is U2. Therefore, A1 equals U2, right? If we look back at that equation, A1 plus A2S. Well, when S equal to 0, we essentially get U2 equal to A1. Again, we need another point boundary condition, point of known. Well, if we're at the other end of our element, we're at U3. Well, that makes us determine that U3 equals U2 plus A2L, right? Just plug in. We know A1 is U2 already because of our first boundary condition. We now get this equation based on knowing that the displacement when we're at S equal to L equals U3. So based on that, we can algebraically calculate that. A2 equals U3 minus U2 over L. So if we plug it all back into S, or use of S, we get U2 plus U3 minus U2 over L times S, right? We know what A1 is, we know what A2 is. What's incredibly valuable to us, right? In the finite element method, we're just discretizing it, separating it into finite regions. We're going to solve for nodal values. And when we have the nodal values, right, which would be U2 and U3, we can then figure out, based on our interpolation function, right, we're assuming that if we know U2 and U3, right, at any given value of S, right, as we move from one end to the other, we can figure out what the displacement is. Right? U2 and U3 then become essentially constants in this equation, right? And what changes is S as we move from one end of the element to the other. And so another valuable form of this equation would be to pull out all of the U2 and U3s, right? And get a function of U2 and a function of U3. So we rearrange this. 1 minus S over L times U2 plus S over L times U3. These guys right here. What are these called, Elias?
Sorry?
Do you know what these are called, these coefficients? Shape functions, exactly. Thought you put all your effort into Ladine's class.
So one of those a U2 and one a U3, are they both?
Oh, would you quit it, Greg? God, you're just calling me out, man. I should call you out on your homework. Huh? Supposed to be a dictatorship here, okay? Yeah, these coefficients are called shape functions. What shape functions are is they relate what the nodal values are to our field value. Okay? So if we're at the very beginning, if we're at S equal to 0, right, this becomes U2. Right? U2 dominates the behavior at the beginning of the element. And as we move to the other end, right, we get diminishing returns, 1 minus S over L of the value at the beginning of the element, and we start gaining value based on the end of the element. And when we get to the end of the element, U3 is dominating, right? We get the nodal value. This is the most simplified version of the finite element method right here, okay? Just want to make sure you know this, because this is what visual analysis is doing, ANSYS is doing, ETABS, RAM, RISA, all of them are doing this, right? Based on selecting an element that has a displacement function, right? An assumed displacement based on nodal values, right? Okay. This is what we would call our interpolation function. All right, 2 degrees of freedom. We get 2 shape functions. All right, we get a shape function for every degree of freedom, because each degree of freedom is going to influence, right, our field variable, what we're trying to figure out between nodes. So in our example here, we're going to solve for nodal displacements. Well, from mechanics of material, this can be very simplified, right? PL over AE. We know what it's an axial loaded bar. If you guys remember that. Hopefully you remember that. So if we use mechanics of materials, this is a very simplified approach to calculating our nodal values, right? As I mentioned, separated up into discrete regions, finite regions, right? We algebraically calculate what our nodal values are, and then each of our finite elements, right? If we select a finite element, that finite element has an assumed field variable interpolation function, right? It's essentially just saying, I'm assuming that if I know the n values, that the value between them changes in a certain manner. So in our case here, right, because it's very, very simplified, when we're going to calculate our nodal values, we're just going to use the mechanics of materials method, okay? There's other methods to do that, and we'll go through some of those later. This is very simplified, right? So displacement is PL over AE. So at U1, right, the very top of our, or sorry, the base of our column, right? Our displacement is 0, right? It's at the base. U2, well, we get PL over AE. But our area in which we're calculating, right, is 6 times the area. So I'm going to shove a 6 in there. So we get negative PL over AE times 1/6. This equals negative PL over 6AE. U3, well at U3 we have U2 plus the displacement across our second element, right, our middle element, which is negative PL over 4AE, which equals PL over AE 1/6 plus 1/4, or we get negative 5 PL over 12AE. Do it one last time, right? The displacement at the top is going to be the displacement at the third node plus the displacement across that finite bar element, right? Which has a length, area, modulus of elasticity, PL over 2EA, because we have 2 times the area, equals negative PL over AE, 1/6 plus 1/4 plus 1/2. That equals negative 11 PL over 12 EA. What's that? Oh, AE to EA? Yeah, sorry. So now we have our nodal values. Eventually, we're going to want to know what our stress and our strains are, right? Our stress and our strains come back from mechanics again. Strain is the change in length over the original length. In our case, our change in length, right, that's our displacement, U. So we want du. S is our variable along the length, right? So we have ds over the change in length. Previously, we knew that we had this function for displacement, which is 1 minus s over L, u2, plus s over L times u3. Really? 950?
Was it 10?
950? What?
Like, is this serious? I mean, yeah, come on, sit down. Have a second with us.
I'm sorry. sorry.
No, that's fine. That's fine. It's a good end of the class. Yeah. That's it. On
I just
Wednesday.
hit the wrong time.
I know, that's fine. I've heard that excuse already once. That's all right. We will continue this on Wednesday. That is epic.
You can't have our first class last semester at 10 and then you make it 9 the next semester.
I guess so.
Should've made it 10 o'clock.